In the last lecture, we had given an interpretation for the Grover rotation, and we had seen that the Grover rotation operator Rg is us times uw. We had seen that what uw does is to invert the particular mark state, and after that what us does is to invert it about its mean, and this becomes an algorithm which one can apply several times to selectively amplify the amplitude of the mark state. I had taken the specific case of the 8 and did the calculation, which is trivial to calculate, and had seen that after one Grover iteration, the amplitude becomes 5 times the amplitude of each of the members of the standard state. The other point that we pointed out is that the maximum number of iterations m, this is approximately pi by 4 times square root of n, showing that with respect to the classical algorithm, this is speeded up quadratically. What I will do today is to try to find out what is the method of actually doing it. We have given the spirit of doing it, but how does one actually do it? And we will see that it is possible to implement it using the elements that we have learned earlier. So let us suppose I have made m iterations. If we have made m iterations, remember my original angle was pi by 2 minus theta, and after every iteration I am increasing the angle between the standard state and the mark state is decreasing by 2 mc. So as a result, the angle between S and W after m number of iterations will become pi by 2 minus 2m plus 1. So if this is the angle between S and W, the amplitude of S in W, sorry, I meant amplitude of W in S, is sine of this quantity 2n plus 1 theta, because it should be cosine that and equal to that, and I can put in the value of m that I just now calculated, that is sine of pi by 4 square root of n multiplied by 2, so it is pi by 2 square root of n plus 1 times theta, which theta equal to sine theta equal to 1 over square root of n. So that's equal to sine of pi by 2 plus 1 over square root of n, which is cosine of 1 over square root of n, and for large n this is given by 1 minus. This is the amplitude, and you can, I had given you a graph of an amplitude, a variation with every iteration for 4096 number of items, but if you have a computer, then you can easily do it for others, and you will find that this is what actually works. Now let us look at the matrix implementation of this. Now in order to do that, what I do is the following. I will define something called a diffusion operator. The diffusion operator or a matrix, I will be talking about the matrix representation, is a matrix, m by n matrix, whose ijth element is given by minus 1 plus 2 by n if I happens to be equal to j, that is the diagonal elements of that, and is just equal to 2 by n if I not equal. Now it turns out, which one can very easily show, that D has the following matrix representation. D is equal to minus I plus 2j divided by n, where j is a matrix, n by n matrix, whose each element is 1. Now, let us see how this happens. It is fairly straightforward for you to prove that if j is a matrix whose each element is 1, then j by n happens to be a projection operator or projection matrix. That is, j by n square is equal to 0. So just multiplying two matrices, identical matrices, whose each element happens to be the same. Now let us look at why this D is of use to us. So first thing that you realize is the following. Notice my D is minus I plus 2j over n. So when it acts on the state A1, A2 up to An, what will I get? First thing to observe is minus I. So I want to find out what is this. So it's an identity. So therefore I get A1 plus A2 up to An with a minus sign, and this J, if you recall, is a matrix whose every element is 1. So what this gives me is minus A1 plus 2 times the average, because 2j by n acting on this, minus A2 plus 2 times the average, etc., right up to minus An plus 2 times the average. So what it means is that this diffusion matrix acting on psi is giving me sum over x 2 times A bar minus Ax acting on x. So therefore, the action of Us I can implement by a matrix, and we had seen, and which I will be talking about later, that once you have given me a matrix, I can always find a circuit or a quantum circuit which will implement. This is the statement I am making. I will not be proving it in my lecture because it requires a bit of a algebra, but what I will do is, the algebra is fairly straightforward, it is a little clumsy, but what I will do is to include this algebra detail in the lecture notes that will accompany my lecture. So I claim, which as you can see from my notes, that the matrix G can be implemented by the following quantum process, where this W is Walsh-Hadamard transform. And R is a selective phase rotation. Wallace-Hadamard transform is simply the extension of the Hadamard operation on a single qubit to the case of many qubits. Recall that Hadamard operator acting on n qubits state x will give me 1 over square root of n sum over y minus 1 to the power bitwise product x dot y y. Now this is simply a trivial extension of the fact that on a single qubit the Hadamard transform gives me 1 over square root of 2 0 plus minus 1 to the power x 1 when it acts on x. That is because acting on 0 it gives you 0 plus 1 by square root of 2, acting on 1 it gives you 0 minus 1 by square root of 2. So what I called as the Hadamard transform has matrix element wij which is equal to 1 over square root of n. This is what implements this times minus 1 to the power I dot. Rij is a phase, selective phase rotation as I told you. Its structure is given by 2 times delta I0 minus 1 delta I. As I told you that I am not going to spend a lot of time in proving this, but for those who are interested, you can look up the accompanying. Okay, once we have made this statement that it is possible to implement the diffusion or the Grover algorithm through the quantum processes that we know. Let us talk about the algorithm. So first what we do is we generate a standard state. If you recall, the standard state is simply uniform linear combination of the computational basis, which is obtained by passing n qubit null vector to a series of Hadamard. This we have talked about several times. The n plus 1th qubit, the ancilla qubit, which is my target, that is initialized to 0 minus 1 by root 2, and once again you are aware I can start with a single qubit 1 and then pass it through a Hadamard. Now I am going to apply now the Grover operation on it m number of times, and m, as we have seen, is a quantity of the order of square root of n. So the way I do it is shown in the slide. So I started with the standard state on line 1 and y on line 2, and so this is simply what happens after it has passed through the oracle. We know that the oracle has calculated f of x, so therefore this is what I have done. Then I apply the diffusion, which we have said can be implemented by d equal to w r w. These two steps, step A and the step B, I apply of the order of square root of n. Now, if you apply the algorithm square root of n times, we had already seen that the amplitude of the Mark state is going on being selectively applied. So what will happen is, if you measure the first register now, then with a very high degree of probability it will identify the Mark state. Remember, what is the idea? The content of the first register is a collection or a linear combination of the inputs corresponding to whatever is there in my target. And in that input, when I measure it, I will get one of the contents with a probability defined by what is the amplitude of the linear combination in that state. And since we have said that on application of square root of n number of iterations, the amplitude of the marked state is significantly higher than the amplitude of the other state. So in all probability, you will find the marked state being filtered out by measurement of the first state. The algorithm can occasionally fail. The probability of it doing so is of the order 1 over n. Now if it happens, then you have to simply repeat that algorithm by going back to step 1. This essentially gives you what you will be actually doing. As I said, that these are the null states which are passed through Hadamard, giving me the linear combination that we are talking about. This is y which is set to 0 minus 1 by root 2. You apply an oracle and then apply the diffusion. The reason why you are seeing this dot 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 is we are saying that this oracle is to be applied square root of n number. Now remember, I am not doing any measurements at all. The measurements will be done at the end of the calculation, when I know that there is a significant possibility of it becoming this. The next thing that I am going to do is to find out what is the quality of this algorithm. In other words, what is the chances of success and the chances of failure. I mean, I have already given you an idea that it's of the order 1 over n that the algorithm will fail. So, look at what is done. We have said that I have a standard state which has a large number, very large number other than 1 of basis states. Now, if you call them by u, then since there are n minus 1 of them, I have normalized that state now. And the standard state is simply the 1 over square root of n w, which has been separated out, and this. The marked state is inverted by the operation t. That is my first state. The application of the diffusion operator, the amplitude of the marked state increases. Now, what we are going to do is this. We are going to say, suppose after jth iteration, the amplitude of each unmarked state is usual. Remember that the unmarked state, since they are all at par, so whatever is the amplitude in the computational basis of one state, the same is true for all the unmarked states, and that of the marked state is w. Now, what we are going to do is that we will now apply the diffusion operator on this state and try to find out what is the amplitude of both the unmarked and the marked state as a result. Take the definition of the D and apply this on this vector. Now, this is a vector which is the state of the system after jth iteration, and so therefore, after jth iteration, this is minus I plus 2 by n j active. This is a straightforward addition here, because each element is 1, the matrix multiplication is easy. Now, when you have done that, you have got a large number of equations, but because of the fact that n minus 1 of those equations are identical, because the contribution of each of the unmarked states remains the same. So, this is basically a pair. This pair of equations are written down here. I have changed the right hand side from Wj to modulation, because we have seen that what the application of T does, that is the application, the step before D, the W gets inverted. So therefore I write W which has been inverted Wj as minus of modulation W, and I convert this into T-W equation. We will see in the next lecture that this pair of equations can be easily solved, and we will get an expression for the amplitude after n magnitude, and that will tell us about what is the possibility of success of this. Having done that, what we will do next will be to take the specific example of n is equal to 8, which we will be in a position to calculate using the operator method. We had already done the n is equal to 8 case, both using the rotation by 2 theta, then using the fact that about the mean it gets inverted, the amplitude gets inverted, and this last thing that we will be doing will be to see how this works for the operator, the matrix.